In stats, we started talking about sample means and the sampling distribution. So we have at the very beginning here a picture of, I believe these are salaries in the graph below, and this is a long drawn out description of different salaries. There are 61,742 households that we're looking at, and their salaries are on the left right there. So that's the population. I'll write that down in a second, but I want to scroll back up. So the population of all salaries is on the left, over here in the left graph. And then it talks about how they take one sample of 100 households right here. So a sample of 100 of these randomly. And they get an X bar of 66,807. Naturally, it's a little different than the true mean. So the true mean of all households is 69,750, and the sample mean is different, 66,807. They do it again right here, and they get 70,820. Then they do it over and over again. This says a computer did it 500 times, and they created this graph on the right. So on the left, this is the population of all households. And on the right, that is a sampling distribution. Of 500 means. So they did a mean, they did a sample, found the mean, did a sample, found the mean, and it piled up like that. What I want you to see is that we have positive skew here. And since they took a sample size of 100, let's add that to this, for n equals 100. Since since 100 is a large sample size, it made a normal shape. I know it's very peaked in the middle, and it's not necessarily bell-shaped, but we're going to call it bell-shaped because it's symmetric and it peaks in the middle and it trickles off on the sides. So anytime you take a large sample and you do it indefinitely and create a sampling distribution, you will normalize the population graph. This was huge when they discovered this in stats, because now you can predict things based on sampling. It didn't even matter what shape the population was, because in the past, last semester, we could only predict if it was bell-shaped. Now you can take any shape distribution, apply sampling distribution properties, which are right here. I believe it was Gauss that derived all this stuff. And then you can predict behavior because you know that it's bell-shaped. It's pretty cool. So in the last handout, we learned sampling distributions, properties of a sample proportion. So they are very similar. So the last handout, we learned that sampling distribution for p hat was the mean was the true proportion, and the standard deviation was the true proportion times its complement divided by n and square root. Now that changes a little bit, and we know the mean of the means is the true mean. So maybe write that to the right. And the standard deviation of the sampling distribution is the true standard deviation divided by the square root of n. Really common for people to get lost and mix these two things up. All right? We learned this last week, and now we're in X-bar world. So now we know that. It's all typed on your formula chart, by the way. All right, let's tackle a problem. I believe it's about wine. So in this one, they talk about odors that wine gives off. And they know that whatever this odor is, it has 25 micrograms per liter for the mean, and it has 7 micrograms per liter for the standard deviation. That's all they tell us. So I know the true mean for odor is 25. I'm not going to attempt to write those units. You can write it out if you want. Someone told me in third period that it's actually mu g, which is just confusing because we already have mu on the board. So I'm just going to leave it like that. And the standard deviation is 7. This problem is very basic. They want the mean of the sampling distribution, and we know the mean of the sampling distribution is the true mean, so 25. Standard deviation, we need to grab the calculator. You take the true standard deviation divided by the square root of the sample size, and we're taking a sample size of 10 right here. And when we do that, we get an ugly decimal of 2.2136. And that's all. That's all that one's asking. All right, let's talk about young women's heights again. So this problem right here is a really good example of why we are able to make predictions and do statistics. They tell us that heights are normally distributed. So let's call heights X for young women, with a mean of 64.5 and a standard deviation of 2.5. So they tell us that in the sentence up there. The question is just stuff that we did last semester. What are the chances that some random woman is taller than 66.5? So this is not a sampling distribution. No sample taken. I mean, you could call, I guess, the one woman a sample, but that doesn't count. That's just one random person. You need like 3 or more, I think, for something to be a sample. So you get the z-score for 66.5, subtract the mean, divide by standard deviation, and you get a z-score of 0.8. You jump to normal CDF, you go 0.8 for the lower, a bunch of 9s for the upper, and you get a pretty likely probability. 21% chance that you get one woman randomly that's taller than 66.5. It looks like the question is the same on part B, but there are 2 different things. What is the probability that we have a mean height for a sample of 10 greater than 66.5? The language changed. A sample was taken. Our new question is, what is the probability that X bar is greater than 66.5? It doesn't look different, but it is way different. We need to find the mean of the means, the standard deviation of the means. Mean of the means is easy. It's not changed, 64.5. That's in your handout. Mean of the means is the true mean. Standard deviation is the true standard deviation divided by square root of the sample, and we get 7906. And then we need to find the probability. I know, by the way, I know it's normal. This step isn't as crucial because the population was normal. So therefore, the sampling distribution has to be normal. It's going to reflect it. It's going to look the same. The z-score changes, though, and instead of writing the z-score for this particular problem, maybe work on memorizing the value in question minus the mean divided by the standard deviation. I mean, it honestly is x bar minus the mean of the means over sigma x bar. That's really what the formula is. But think of it more like value in question minus the mean divided by standard deviation. Because you don't want to accidentally divide by only 2.5. You want to make sure you divide by the adjusted standard deviation of 7906. Because we get a big z-score compared to the last one, 2.5297. Way different from 0.8. And when I do normal CDF, I get a tiny probability. All right. I hope that made sense. I will see y'all later. Bye.